All right. Good morning, good afternoon, good evening. Um, for this talk, the slide, the file name is FNE32 group learner PDF. So far we have talked about a few things. So let me move to the big picture slide. So we saw this 2 days ago. For typical fMRI analysis, it involves four stages. So first we design experiment, then collect the data. Then we have the pre-processing steps. Yesterday we talked about a lot of that content. Then the third stage, modeling. Today we're going to focus on group level. That means we have done for each participant, we'll analyze their data using a regression model. So we go to group level, then we build a model, then say something. So the last stage would be a result reporting. Before we talk about the specifics about group level analysis, we want to say something about big body statistics in general. So the dominant approach in fMRI, particularly, is adopt the traditional framework. It's called a null hypothesis significance testing, HST. So when we say statistical inference, what do we mean? So we want to say something about results based on the result, right? So usually it boils down to p-value or t statistic or z or f statistic, right? So fMRI, most of the time, people ignore the body response amplitude, focus on the statistic, and that further is banalized, right? So either you say each brain region is either associated or engaged to some extent to the tasks. That once you binarize the results, we ignore the uncertainty. But in reality, regardless how strong or weak your evidence is, there is some extent of uncertainty. That extent of uncertainty is typically ignored when people write up their results. So that creates some problem. So let me review a little bit about the traditional statistical framework. So null hypothesis significance testing. So the rationale is that regardless the well response magnitude, we pretend there's no effect. So that's why you say the horizontal line, the blue line. So the x-axis is the p-value in this case. So we even regardless how much evidence you have, we pretend that there's no effect. So now you calculate p-value. So the vertical bar, we say that is some threshold. That magic number is the typical decision boundary, right? So on the left-hand side, okay, then you say the evidence is strong enough, you feel comfortable to make some statement. On the right-hand side, we show the evidence against that null hypothesis, right? So the well case, the effect or some distribution. That distribution depends on the magnitude of the effect. So the green one is strong, right? So that's why most of the distribution is on the left-hand side of the threshold bar. But if the effect is small, the red one, then we would have trouble to survive, right? That threshold. That will create a problem. That problem is if we dichotomize the results, okay, the less then we can control the so-called false positives. But we pay the cost. That cost is called false negatives. That is on the right-hand side, the two distributions is they are the light colored, the right tail. For the big effect, yes, they were willing to pay that false positive. But if the effect is small, we're going to lose a big chunk of the evidence, not the evidence, the opportunity to detect. That creates another problem, right? If you look at the red one, on the left tail, yeah, we would have a small chance to survive. But that surviving part is only if the effect is big enough. Here I want to distinguish the problem. We don't know the ground truth, right? The ground truth is 0.2 is small, but you may by chance, you may detect it's like 0.8 or even bigger, right? So that would survive the thresholding. But that creates a problem called type M, because the magnitude is bigger than the ground truth. Since we don't know, but by chance it could end up have a big effect. So once you filter using threshold, that creates a problem, right? So that is part of this strategy if we treat the statistical inference as a decision-making process. So that's why in the field we have this we produce a problem simply because we filter, we set a threshold bar, we artificially dichotomize the evidence. So that is a big controversy in the field in statistics in general. So applied this problem to FMI is that people tend to treat the individual study as some decisive process. So in the end, either you have the surviving clusters or you don't, right? So once you set the threshold at the cluster level, then you treat it as a decision-making process. But in reality, there's uncertainty. Well, that uncertainty is expressed as the continuous information. Even if we express as a p-value, the p-value is also continuous. So in reality, the evidence is continuous. It should be cumulative, not absolutely conclusive. But that continuity is lost whenever we dichotomize the results. So that's the problem. Can we do better? Alternative approach is called estimation. Instead of focusing on decision making or testing, we focus on estimation. What do I mean by estimation? By estimation, we present the effect magnitude and the uncertainty. So that's a different angle. So that will help us to be mindful about the uncertainty and help us enhance reproducibility. So if we use this 2x2 matrix to express this different angle, so the vertical is we either treat it as a decision or as estimation. Then there's two modeling approaches. One is a frequentist, that's the dominant one. There's a Bayesian approach. So regardless what the modeling approach we adopt, I think it's better to adopt the green one, the bottom row instead of the upper row. But currently, the dominant approach in FMI is the red one, treated as a decision-making process and adopting the traditional framework of a frequentist. So using a non-hypothesis significance testing, focus on the p-value. We will try to say if we adopt the estimation approach, should we do, what can we achieve? So this is another angle to visualize the problem if we treat the statistical evidence as a decision-making process. So on the left-hand side, you see two results, right? So the blue one and the red one. If we only focus on p-value, the left tail, the blue one, the p-value is small, right? So under the non-hypothesis significance testing framework, we would say this evidence is strong. In contrast, the red one is weak because the p-value is 0.09, right, with a large survival thresholding. But if you look at the distribution for each of the two effects, most of the time, the red one is bigger than the blue one. So this indicates if we focus on p-value and while we ignore the magnitude, we will reach a conclusion that probably it's a little bit, we lost a lot of information and would create a problem, right? That problem is even though the red one is bigger, but that would be filtered out. We will not even able to see that, right? On the right-hand side, both effects have exactly the same extent of evidence. The p-value, the one side the p-value is 0.02. But still, again, the orange one is most of the time is bigger. So both cases tell us that the p-value itself is not just one piece of information, is not complete. Because if it fully ignores the magnitude, well, not fully, but at least we don't, the p-value does not directly encode the magnitude. So we need two pieces of information. One is the magnitude, the other one is the uncertainty. So the uncertainty under the traditional framework is confidence interval or standard error. Under Bayesian framework, we would focus on the whole distribution. So that would be a one-dimensional information instead of a single number. Now let's talk about the variability, the different sources of variability in FMI, right? So one big source is about cross trial, right? So each task, we usually design experiment with many representations, right? So for example, happy face, we would probably put it 20 or 30, depends on the experiment design. That currently, we create a regressor assuming all the trials have exactly the same magnitude, right? So that's the assumption. And that's just for the convenience because we only care about the average across all the trials. So suppose we have 20 trials, then the cross-trial variability is fully ignored. Is that a problem? Well, most of the time it's okay if the number of trials is big enough. If the number of trials is small, can be problematic in two aspects. One is the sample size is small, the cross-trial variability may be, the estimation may be inaccurate. Other problem is more from science perspective. If you only have 10 trials, those 10 trials may not be a good representation for the phases, the happy phases. So that's the cross-trial variability. Then there's cross-individual, right? For the number of participants we include, of course, they are different. Each participant is unique to some extent. They don't respond exactly the same way. So we need to make assumption. That assumption usually is Gaussian, but sometimes it's not good enough. Maybe sometimes can be skewed. That may be a problem. Then the third one is the cross-brain. Well, that's understandably cross-brain are different. Each brain region responds different to some extent. But the current approach, we use a massive univariate analysis. That is that we treat each voxel behaves independently relative to the rest of the brain. Even among the liver voxels, we assume there's no relationship. So that creates a problem. That problem is, first of all, have the information loss because we assume they're totally independent with each other, but that's not true. The second problem is the classical multiple comparison problem, right? So because we, under the traditional statistical framework, by chance, that's the argument is by chance you would have, even if there's no effect, it's a zero, then you by chance you would end up with a strong evidence among, for example, it depends on how you set up the significance level, right? The other problem across the brain is the hemodynamic response, the so-called HRF, right? Most of the time we adopt the canonical HRF, but we already know each brain region may have their unique response shape. So that approach may create another problem, right? So that we may have the identification sensitivity problem. Then there's a cross pipeline, different pre-processing, different software packages, different modeling strategy, different reporting styles. That create another variability. So that is for reproducibility, not necessary for each particular study, but that's for the whole field. That creates a problem. Then for the model, different model strategy, that will be minor for that. The model, I mean, you can argue it's just a regression at the individual level, at the group level, it's just a one simple t-test. But it can be complicated. Why? Because the model has some impact. Then there's a lot of issues we need to deal with, as we can later see. For example, one is the hemodynamic response at the individual level. Do we use canonical HRF, or are we going to use a data-driven approach, estimate HRF? So that will have some impact, right? Then how to handle multiple testing issue? That's another problem. You're going to analyze voxel separately or analyze at the individual level using a list of RIs. So those are the different sources of variability we need to take care of. So now let's talk about the group level specifically. Let's clarify a few terms. So group level usually involves some factors. Unlike individual level, it's a regression model. So usually you have regressors, you have those covariates like head motion. At the group level, we deal with different aspects of those variables. The typical one is the factors. What is a factor? A factor is a discrete variable or categorical variable, right? So that can be within or between individual variable. So for between individual factors, typical one, males versus females or patients versus controls. So those are the typical factors. We categorize it as between individuals. Then there's the individual. Well, within individual factors are typical task conditions. Suppose we have emotion factor, we have 3 levels, happy, sad, and neutral. So we have 3 levels. So we have the concept of different levels. What's the difference between individual versus within? The between is from modeling perspective, they're independent with each other. There's no correlation between them. But for within, they are related to some extent. So we need to take care of in terms of modeling because from the same participant, those 3 levels that are correlated to some extent. So that's from modeling perspective, we need to be careful. Then there's a quantity variable. Sometimes we call it continuous, right? In some contexts, people call it covariates. That depends on how people use this term. So quantity variables can also categorize it as within and between. So between, if it's a cross-sectional study like age, each participant, when that participant is scanned, at that particular time, there's an age variable. Right? Other typical one, the watch time, brain volume depends on cortex thickness, for example. Right? So each individual has a unique number. There is a within individual. That's if it's a longitudinal study, the age can be within individual variable. Right? It's a quantity variable. Then sometimes people have other like a rating. Rating like you have 3 conditions: happy, sad, and neutral. Then each one you have a rating. I mean, how happy you are for that particular task. Then we have covariates, right? Covariates, usually it's the variables of low interest. That term is also a little bit ambiguous, depends on the context. Some people use it as all the experimental variables they use for that, or quantity variables or variables of low interest. That covariates is usually people just, especially if it's variables of low interest, it's something can be a slippery. We will talk about why that's we need to be careful what kind of variables we should be included as a covariates. Then there's a concept of fixed versus random effects. That's specifically for the notion of a linear mixed effects model. So the word mixed, that means we have both types of variables, fixed versus random. Fixed, I mean, literally means constant in the model, right? So that's typically like task conditions or between individual factors. That people, what do we mean by it's fixed? That means we focus on the group level. So the group average is we considered as a fixed. So in the model, it's a constant term. But in comparison, the random effects, it's not a constant. It's a varying term. That vary depends on the variable. For example, The typical one is the participants. So participants, of course, each brain region that varies. So some participants may have higher than the average, the others may have lower. So how to handle that? Since it's a varying term, then we need to associate that with a distribution, typically a Gaussian distribution. So that's the difference. So in the model, fixed effects is coded as a constant parameters. Quantum effects, there's also parameters, but there are parameters, there are distribution associated with each quantum effect term. Our model structure, right? The most popular one is a student T, right? So one sample paired, two sample, probably most of the time that's what you would use. But sometimes we need to use another structures. For example, general linear model, that is when you have covariates, you have a continuous variables. So we use general linear model, or we may use ANOVA and COVA. So you have one or more factors, and sometimes you have continuous variables. Then you have hierarchical models. That's a linear mixed effects model, for example. That's one possibility. Then I want to mention a little bit about the R notations, because that in FNA we use some of the group level programs. We need to specify the model structure. As model structure, we use the R notation. R notation, if we have two variables, for example, in this case, A and B, most of the time it's factors, but occasionally we have quantitative variables. Suppose we have two variables. So A star B, we expand that into four terms. We have the intercept, then we have the main effect of A, main effect of B, plus the interaction between the two. The interaction expressed as the colon between the two variables. That's the so-called fixed effects. That's at the group level. Then at the lower level, that's usually we need to specify the quantum effects. The quantum effects is specified like this. Use the parenthesis. Then there's a vertical bar on the left-hand side of the bar. Is we put the you usually put the intercept, the one pretty much like the fixed effects. The ones stands for the intercept. Sometimes we also put it not just the intercept, we also need the slope. That's like a longitudinal study, for example, age. That sometimes we need to put 1 plus age, for example. Then we also have in the second case, the quantum effects here, on the right-hand side is the the interaction between A and the subject. So that means for each subject and for each of this factor level, we assume there's also a varying intercept. So that's a notation. So this table gives us the typical the list of the group level analysis programs. So the first one, 3D t-test plus, that's the most popular one. So we use that to analyze the typical t-tests, right? One sample, two sample paired. Some types of general linear model, we can also use 3D t-test plus. The second program, 3D MIMA, that's pretty much the 3D t-test plus version, but with the only difference is for the 3D t-test plus, we only take the regression coefficients from the individual level as input, the beta weights. We ignore the t-statistic value. For 3D MIMA, we can take both the beta plus the t-statistic as input. Why is that? What's the advantage? We'll see why we would do that. So the next program, 3D MVM, that's pretty much we use that for general linear model and ANOVA and COVA. The next one, 3D MER, that's a linear mixed effects model approach using the R package, LME4. So that's for hierarchical modeling. Next one, 3D GRMM, that's relatively new. That's I would say it's pretty much the most inclusive model, except that the difference between this and the 3D MER is we don't need to make an assumption about the residuals, the Gaussian distribution. We can use, for example, to handle, presumably if you suspect your data may have outliers, you can use 3D GRMM to use the option student T distribution for the residuals. That will be able to help you handle outliers. Next program, 3D MSS, that's for the case that typically if you assume there's a nonlinearity. Particularly, this program can be used if you analyze model the hemodynamic response profile at the individual level instead of using canonical HRF. So at the group level, we would use 3D MSS to handle that scenario. So the next two programs, 3D ISC, that's for laterally scanning. So that's like typical like listening to music or watching movie. So that task is continuous. So that case, you will have a program called 3D ISC. Next program, 3D ICC, that's for typically for we test reliability or intra-class correlation. So those programs are for voxel level. The last three programs for RI, RBA, that's for suppose we have a list of RIs. We use this for using the Bayesian approach, which we'll talk about later on. The PDA is for the profile trajectory analysis. That's the RI version of 3D MSS for nonlinear model. You analyze for each RI separately. The last one is the test with test variability for each RI. That's the RI version of the 3D ICC. So there are a few other programs that we will not talk about. If you are familiar with them, you can continue to use them. But since we don't have to use them, they are just a little bit outdated. So let's start with the simplest case, t-test. Technically, you don't need to understand the modeling part, right? So you can just suppose you have one group of participants, you have one particular contrast or effect. You go to group level, you put those beta values from each subject, then provided the program will solve it. But maybe it's helpful to understand about the underlying mechanism, right? So even we don't need to fully understand, but at least some extent of understanding is important. For example, the one sample t-test. At each voxel, we have the data. So, so that's the, excuse me, the y sub I. Then the model is basically we decompose that each data point as two components, is the group average plus the residuals. So the only information is the y sub I, right? So, but we decompose the two into two components. Then we use pretty much like the regression model, use ordinary least square to solve it, right? To solve it, we can estimate the average of plus the participants. So that's the average. Then there's the uncertainty information. That's the standard error of the average. So the T is basically the group average divided by the standard error, right? So that helps us understand how the T statistic is computed. So the program in Affinity is 3D test plus. Later on, we will see a concrete example. So that's the modeling part for one sample t-test. Paired t-test, why it's called paired? That's because usually we have one group of participants, but then we have two conditions. Suppose happy and sad, we want to compare the two, right? So happy versus sad. So each voxel and each participant, you have two data points. So the model is pretty much the same as one sample t-test. Why is the same? Because since we are interested in the contrast between two, we just internally, even though as a user you provide the two beta values, but internally the program basically the contrast of the two, then you plug into the same model as the one sample t-test. So the program you just add the option, the dash paired. The next one is the two sample t-test. How is that different from the pair? Well, instead of have each participant have two effects, we only have one, but you have two groups of participants, presumably males versus females or patients versus controls. So in this case, the model is different. So we need two indices to code those two data points for one data point from each participant. We use the parenthesis, the index, to indicate each participant is either one group, the other, but not both, right? So that's why it's called a between individual factor. So the model is different from the one sample t-test is because we have two indices, right? So that's we need to handle the residuals a little bit differently. So in this case, it's a special scenario of one sample between individual ANOVA, or you can call it a general linear model, but the general linear model just have a special case, have a slope. That slope is basically the difference between two groups. The program, there's an option called -z skip. That's usually if you have you want to exclude the zero values because especially along the mask, then some participants may have missing values. So those voxels a little bit tricky because if some participants you have values, some participants don't. If you just use all the values, then you will get a biased estimate, right, for those voxels. So this option will basically exclude those zero values, only model those participants with the real values, with non-zero values. So that will give us a little bit accurate estimate for those voxels with Bayesian data. So that's 3T test plus plus. Then we talk about another program is similar to 3T test plus plus, is the 3D MIMA. What's the difference? The difference is that we take into consideration of the uncertainty. So the typical way, we only take the betas, we ignore the t statistics. Is that justifiable? Well, that approach, we usually assume the uncertainty information is the same across all participants. That's not usually the case, but how big is the deal? Well, let's take a look. Suppose we take both beta and the t statistic value as input, right? So that's the input data, the beta hat, that's the estimate. So the model, we can build a different model. This model will have three components. So the input beta is decomposed three components. Suppose we know the true value, right? Then each participant has a different from that true. The error. Then that each individual, the true value can decompose the group average plus the residual. So we have the model. If we combine the two terms, we end up with three terms, right? So we have the group average, then the cross participants random effects plus the residuals. So we can solve this. This model is pretty much, if we are familiar with meta-analysis, it's the same model. So we have two random terms. So the cross participant variability, then the residuals. If we solve it, then we can get the similar results at the 3T test plus plus. Then this program is called 3D MIMA, mixed effects multi-level analysis. It can also handle the missing data similar to 3T test plus plus, the option Z skip. In this case, called the missing data. Here we look at a concrete example. So using 3D MIMA. This concrete example, so we need to provide both beta and the t statistic as the input. And we can use, for example, here we say the missing data set as 0. So that will handle the particular case when we have missing data using assuming the missing data is coded as 0. So the next modeling framework is called general linear model at group level. So this is a little bit different from the term, the acronym used in the literature. People use general linear model (GLM) for individual level. Individual level to me is more accurately called a regression, not general linear model. I mean, what's the difference? General linear model historically the acronym was created to indicate that in the model you have both quantitative variables and factors, categorical variables. So it's a mixture of two. That's typically the case. This basically is a special case of ANCOVA, right? I mean, it's the terms is just a historical reason. It's a little bit mess. The model is pretty much we can treat it as a regression at the group level. But this, whenever we have a quantitative variable, we have to be careful. There's a centering issue that we need to take care of. We will talk about maybe a little bit later on. Then another issue, whenever we have a quantitative variable, especially we have a covariance, the variables we are not interested in, how to decide what covariance we should include. This also related to the experiment design, right? Why? Because quantitative variables, there are quite many of them, right? So you decide like age, do you need to include that? Or some other like emotion, right? When perform the task, do you need to include their rating as a covariate later on? So during the experimental design stage, you also need to consider that because that will decide what kind of a covariance you would include at the individual level, at the group level. So that's why it's very important to think about it ahead of time even during the experimental design stage. General linear model, we can use 3D t-plus. There's a option called a dash covariance. You can use that to include quantitative variables, but more generally, you can use 3D MVM. Now we talk about in the field, the acronym general linear model is also used at the group level. That creates a little bit problem. So let's use one case, handling within individual design. For example, suppose we'll have one factor, it's an emotion, happy, sad, and neutral, right? So we call this within individual or within subject factor. Some people call it repeated measures, right? So they mean the same thing. So it's a within. So if you look at the model, each data point, so there are two indices, right? I is for individual, K for the factor level, right? So either happy, sad, and neutral. In this case, we decompose each data point into three components. So for each emotion, we have that particular average at the group level. Then we'll have each individual has their particular intercept, right? So that's typically we call it random effects. Lastly, we have the residuals. So we decompose each data point into those three components. So we solve it, then we get the estimate. The first term, we call it fixed effects. It's a constant. The second term is a quasi-individual variability. We assume it's a Gaussian distribution. It's a random effects. Last one is just the residuals. So this would be, in a traditional statistical modeling strategy, this would be called a one-way within subject or period measure ANOVA, right? But in some software packages, this is modeled as a general linear model. The problem with that framework is that if you are focused on the contrast between two levels, for example, happy versus sad or sad versus neutral, that pairwise comparison is fine. Or if you want to say the omnibus test, the F statistic, you want to say any differences across the three conditions, that is also fine. However, if you use the same model to estimate each particular level, for example, happy, you want to estimate happy or sad separately, that this model will break because this component would be gone. So you would need a separate model if you really want to estimate each particular emotion task. However, if you use general linear model, this single model to handle all the scenarios, including those individual effect testing, or even have other cases, you have two groups. Use the same model to estimate the group differences for each particular task. That will also be problematic. So this problem has been pointed out a long time ago, the first time was 2011 during OHBM. Even at that moment, the problem had been pointed out, but this problem still persists in the field. In some software packages called factorial design, because they use this same single model to handle all scenarios, that will lead to a big problem. So that problem still persists to this day. So in Anthony, so we handle this scenario, the many different strategies we'll talk about later on. So that's why we need to move to the next modeling framework is called ANOVA, right? Especially when we have repeated measures factors. That's like happy side neutral, right? So that's one single factor. So the previous example, we can move to this ANOVA framework. So it's one way within individual. So ANOVA, again, we have this previously, we say there's three components. Actually, we have four because we put the intercept as a baseline. So we have four components. So those blue ones, the intercept plus the differences related to the intercept, that's at the group level, right? So the lower one, this is sometimes we call it hierarchical modeling because they're multi-levels. Sometimes we call it linear mixed effects. We have both fixed and random effects. Another angle is called hierarchical because there are multiple levels. So the blue terms at the top level is at the group level. This orange one is is the lower level. It's at the individual level. The lowest is the interaction between each level, each factor level, and the individual. So that's the interaction, or the further lower. So three levels. So that's one way. So now suppose we have two way within individual ANOVA. So that means we have two factors. Both factors are repeated measures. So if you use the R notation, this would be the model structure. So we have four terms for the fixed effects or constants, right? So the intercept plus the two main effects plus the interaction between those two factors. Similarly, the random effects or the lower level, we also have four terms. So the orange ones, you can say for each participant, you will have the intercept and the two interactions, right? So for each individual will have the factor A and factor B plus the three-way interaction. So that is three ways, the residuals. So we can treat it as ANOVA, right? ANOVA in Anthony, the old programs, you can either use 3D ANOVA, 3D ANOVA 2, 3D ANOVA 3, right? So that's the old ways. But nowadays, we don't usually treat it as a ANOVA, but we can treat it as a general linear model. That's the other software packages. In Anthony, we treat it as a multi-univariate general linear model, or as a different way to describe that structure. So for example, we use this as a concrete example. Maybe we should take a break here. And let's take a 10 minutes break. Then we'll come back, talk about the script using this ANOVA structure to handle this scenario. All right. So during the break, someone asked about the problematic aspect of using general linear model to handle within individual factors. So I posted a paper in 2014, the paper that explains from the modeling perspective. Probably that's still, the paper also showed the differences across different approaches. For example, using SPM's factorial design versus using the multivariate modeling approach. So here I want to using a more intuitive explanation. So let's back to look at this slide again. Suppose we have one factor, happy side and neutral, or even have two conditions. The problem is the same, right? So in this case, look at the model, we have three terms. So at the group level, we have the average for each condition, each emotion condition. Then we have the cross-individual variability. That's we usually call it random effects. So since the I is the individual, so that term varies across individuals. We associate that Gaussian distribution. The next term is the residual, or you can interpret it as the interaction between individual the participants and the emotion factors. So that's why we use two indices. So those three terms, if we solve it, right? So this is a constant, this is a random effects, this is just residuals. Fine. Then what can we do with this program? We can estimate the individual, then individual emotion effect, then make assessment about the uncertainty t-statistic value for each emotion task. So we can use this to compare to pairwise comparisons, right? So that's valid. We can also say the omnibus test across all the three conditions. Fine, those two scenarios, it's legitimate. However, if we focus on one particular emotion task, the problem is once we focus on one, so the K is fixed. Suppose K equals 1. Look at the model. If a K is 1, then this so-called random effects and the residual, they would collapse. You will not be able to identify because they're identical. So if your goal is to estimate to say something about a particular emotion task, then it's unidentifiable. But people still continue to use the full model, then they use the residuals from the full model to make assessment to say something about uncertainty the value for each particular task, then that creates a big problem. You pretend those two terms are differentiable. In reality, they are not. So you need to create a separate model if you really want to say something about each particular task. So that's the problem is you use the whole model, the residuals are underestimated. So the t-statistic value would be inflated. That's basically the essence, another way to explain the problem. So those two, the full model we decompose into three components, but if you, for each particular task, we will be able to only have decomposed into two components instead of three. So that's another way to look at the problem. Okay, I hope that provides a little bit more an intuitive explanation. But if we why they're using the general linear model to handle within individual variables is problematic when you look at some effects. So that's a simple scenario. More probably common problem is you have a so-called factorial design. That's the popular term. When you have two factors, when you have, for example, in this case, we have one within subject factor, then suppose we had another factor is group, right? So male versus females, controllers versus patients. Then when we look at the group comparison overall, then that's also problematic. Or suppose you have two within subject factors. Suppose you have emotion, then you have a categorical variable like image versus sound, for example. You have two factors. So if we build this full model with two factors, then if you want to look at each individual factor main effects, then this model, that full model, use the full model is also problematic. So it's all bunch of problems. So here I'm just using the simplest case with one within individual factor. Right, let's back to where we stopped. We're here. So this case, we have three factors. So suppose we have one within subject factor. Then you have then suppose you have two within subject factor. Then you have then suppose you have two factors. So if we use build this full model with two factors, then if you want to look at each individual factor main effects, then this model, that full model use the full model is also problematic. So it's all bunch of problems. So here I'm just using the simplest case with one within individual factor. Right, let's back to where we stopped. three factors. The first one is the between individual factor group, patients versus controls. Then we have two within individual factors, intensity, and then we have condition. Intensity, we have high intensity, low intensity. Then condition factor with three levels, positive, negative, and neutral. So we can describe this as a 2 by 2 by 3 mixed ANOVA. So 2 by 2 by 2, that means those three factors. First one has two levels, second has two levels, third has three levels. The mixed means we have two types of factors. One, because we have one between individual factors, then we have two within. So it's a mixture of both between and within factors. So that's the term, I mean, the phrase we sometimes we use to describe the structure. So there's a ANOVA, but there's the three factors and mixed types of factor. So we treat it as ANOVA, we can use 3D MVM. So 3D MVM, multivariate modeling approach. Basically, it's using to handle whenever we have ANOVA, regardless what kind of factors we have. And we can also use this program to handle you have between individual quantitative variables like age. So in this case, we have three factors. So let's talk about the bottom of the script. So the data table. So data table, the first column will provide the subject IDs. The last column we provide the input files. So the data table, the first row of the data table is the column names. So for each column, we provide the content for that variable, right? So the first column, subject ID, last column is input files. So in this case, a lifty file. So in between, we provide all those experimental variables on the right-hand side of the model equation. So in this case, we have three factors. So we have the between individual factor group. So we use the letters to code the factor levels, either control or patient. So then we have two within individual factors. The intensity will have high and low. The condition factor will have three, right? Positive, negative, neutral. Sometimes people use dummy code factor levels, right? So you can use 1 versus 2 or 1 versus 0. I don't recommend you doing that, but if you do it carefully, it's fine, but I don't recommend because for a couple of reasons. One is it's not intuitive. Maybe at the moment you write a script, you remember 1 means patient, 0 means control. It's fine, but after a while you may forget. That's one problem, right? So it's not informative. Second of all, it may mix up whether it's a quantitative variable as a factor. So those are the two main reasons to avoid using the dummy coding. So that's a data table, provide the information about those variables. So now let's look at the upper part of the script. So we typically use, in FNA, use a prefix to specify the output file name. It will use that to attach the whatever, in this case, is a lifty. So the output file will say output.lifty. If we use the FNA format, it would be, for example, Pastelarak, right? Then the next option, jobs. If you have multiple CPUs, in this case, we can take advantage of 16 processors to to speed up, use the parallel computation. So the second row, we specify the variable types. So remember I have three factors. So use -bs vars. So between subject variables, only have one group. Then ws vars within subject variables will have two. So it's intensity and condition. Notice that we use a star to code the two variables, right? So the star, remember in R notation, that means we want both main effects. So if we expand this, we would get the intercept plus the two main effects plus the interaction between the two. Right? So if you don't want the interaction, you would put a plus instead of a star between the two variables. So the next line, it tells us the program we need. If we don't want any specific comparisons, we just want the main effects plus interactions, those F statistics, then that's it. The script would be enough. But probably almost all the time we want some particular comparisons or single effects. So the third line basically tells the program we need 4 particular comparisons. So then the first one, after the first one, basically we want there are 2 options. We need to specify each contrast or each effect estimation. So the first one, we use the label, then we use the coding, right? So the label tells us we want a patient. For the patient group, we want to look at the positive effect, positive emotion effect. So this is the single effect. It's pretty much like a one sample t-test. We focus on one particular group, one particular task. So you can use a one sample t-test to get this. But this is one full model, you get probably almost all you want. Alternatively, you could one sample t-test for this particular effect estimation. So how we code it, so we use this colon to specify. Before the colon, we specify each variable. So in this case, we fix the group to the patient group. Right? So the group is a factor for patient and control. So in this case, we only want to look at the patient group. So for the coding, we use the weight before the star. The 1 means most of the time we use 1. Occasionally, if you want to use the average, you may use 0.5, for example, the average between the 2. But the other cases, usually the weight is 1. After the star is the factor level, right? So this case is patient. So that's the group factor. The condition factor, so for that, we put the colon. Also, we need after the colon, we need a space. If we don't need a space, the program will not be able to identify that's a factor coding. So for condition factor, we fix on the positive emotion. So we put a weight of 1. So that's this simple case. The second case is a comparison between positive and neutral fixed and the control group. So if we look at the coding, is a group fixed and the control group, the condition. So now we have 2 conditions, positive versus neutral. We assign the weight 1 to the positive emotion, minus 1 to the negative. Right? So the label is usually, that's whatever you feel is a label that is informative enough, right, to reveal what you are. Later on, because the output, that label will give us what that is, each effect is estimated is. So the third one is actually it's an interaction, sort of an interaction. So we want to look at we ignore the neutral condition. So basically it's a 2x2 ANOVA structure. So look at the contrast between positive and negative, and that contrast, what's the difference between the 2 groups? So that's why it's a 2x2, it's an interaction effect. So you would get a F statistic if you run the traditional 2x2 ANOVA. But in this case, because both factors have 2 levels, I mean, we focus on, even though the condition factor has 3 levels, we focus on 2 levels. So this would be can be expressed as a t-test, even though traditionally we would treat it as a F statistic. So the last one, the number 4 estimation is another 2x2, but now we focus on the 2 within individual factors. So the intensity, we want to compare high and low, then the condition also positive and negative. So this would be a 2x2 interaction. Again, this can be, you can analyze this as another separate model 2x2, right? But this single model will give us this 2x2 omnibus. It's a t-test as well in this case. So that's this specific data structure can be analyzed as an ANOVA. Alternatively, we can treat it as a hierarchical modeling approach using 3D RMER. So the model is pretty much exactly the same, but it just conceptually we treat it different. So if we look at the model structure at the top, so we at the group level, top level, the hierarchical structure will have the intercept of two main effects plus the interaction. At the lower level, we also have four components. So we have the intercept for each individual. Then we have the interaction for each individual for the factor A, the interaction for each individual at factor B, and the three-way interaction, which is the residuals. So if we treat it as a hierarchical model like this, we can use 3D MER. So the data table at the bottom is the same, right? So it's just same input information. The main difference is the model specification. So in this case, we don't specify the variable types. Why? Because we don't have quantity variables, just factors. So the program, as long as you don't use the option called quantity variables qvars, so all variables will be by default treated as factors. Even if your dummy code use zeros or ones, for example, you would still be treated as factors. So that's why we don't need to specify variable types. Only if you have quantity variables, yes, you need to. So the model, look at the model specification. So we have three factors. So we write all the three together. So you have group. The model here, we ignore the group. The model's formulation, I didn't put the group there, but just for simplification. So in this case, we want a three-way interaction. So that's why we have intensity, star, condition, star, group. So suppose you don't want the three-way interaction, the group treated group as a covariate, you can change the second star as with a plus instead of a star. So the rest is, you can see they are those orange ones, the correspondence. So the parenthesis one vertical bar subject is basically for each individual subject has a varying intercept. Then this is the interaction between the intensity factor and the participants. So I will want them intercept. That's the same thing for the second factor, the condition factor. The residuals we don't need to specify because by default we also have residuals. So once that's why we need to somehow to some extent have this notion of the model structure. Then we can map the model to the model's specification when we use the 3D MER. So that's different from the ANOVA structure, right? So ANOVA is more like a technically we don't need to pay attention to the model structure. We just specify the variable type, either it's a between subject factor or it's a within. So under the hood, the model is basically similar to this, right? So but it's just conceptually it's a little bit different. Either we treat it between subject versus within. Here we treat it as a hierarchical structure whenever we build a model. The next one, I want to briefly talk about intersubject correlation analysis. This is for lateral scanning. So this is it's a niche part of the fMRI studies. So that's usually for movie watching or speech or music listening. So the task in this case is just continuous, unlike the typical fMRI studies where you have concrete, right? So you show a face or push a button. It's like multiple trials. So in this case, it's a continuous. So we cannot, most of the time, we cannot create a model, concrete model to say like an individual level, you have a particular task because this is a continuous. Most of the time, you at the individual level, you do use a regression model for this case, but that modeling purpose is just for denoising. You use that model to remove, for example, head motion, typically a slow drift. then use the residuals as your input for the second step at the individual level to calculate the correlations. The correlations in this case is a lot about each particular participant. It's about pairwise. So how similar each pair of participants, how similar at each brain region their responses. Right? So that's why it's called the inter-subject correlation. So for each subject pair, you calculate the correlation. Then that correlation, we need to summarize at the group level. So the complexity is that even if we have 10 subjects, we end up with many pairs, right? So with 10, you can calculate the combination, right? 10, we would have 45 pairs. So in this, on the right-hand side, I show a case of 5 individuals. 5 individuals, the combinations will have 10 pairs. So end up with 10, for each voxel, we have 10 correlation values. How do we perform such a group level analysis? Right. So each pair, those 10 pairs are not independent with each other. That's why this matrix shows the complex correlation structure for those correlation values. So it's a little bit complicated. So that's why this program 3D ISC was created to handle that scenario, because those pairs are not independent of each other. So there's a hierarchical structure. That hierarchical structure is shown in this model formula. Right? So each pair we decompose into 4 components. There's the group average, that's the blue one. The orange one is each participant contributes to that component. So that's the tricky part. So in the model structure, then I have the residuals, which is the interaction between each pair. So this program is pretty much similar to the MER, but it's just the interface is a little bit different. So this basically shows at the bottom, it shows the data table. So since we have the input is a pair, so we need 2 subject IDs. Then last column is the input files. Then in between, suppose we have depends on the group, right? Suppose we have 2 groups. How similar within each group, or the group 1 and 2, how similar between 2 different groups. For example, typical ones, males and females, or child versus their parents, right? So that's also a popular scenario for inter-subject correlation, right? Especially the child versus how similar to their own parents, or versus their stranger parents, right? So that you can get it complicated like that too. So this is a pretty niche study scenario. Next one, let's move to nonlinear modeling at the group level. The typical one is the hemodynamic response function case. So 2 days ago, we talked about the modeling at the individual level. Most of the time we use canonical HRF, right? That's simple, straightforward, but there's a caveat. That is that HRF is fixed. There's a low flexibility. So the peak is always at 5 seconds. The undershoot is also fixed relative to the peak. Suppose we use the other extreme, data-driven approach. We estimate the hemodynamic profile at the individual level. So once we reach the group level, how do we handle that? One scenario, we can use the peak, right? But that's also a possibility, but even that peak is a little bit tricky. How do we extract the peak information? Because that peak varies. But the data at the individual level, we put in multiple tens. That tens is a discrete. Every 2 seconds, for example, get an estimate. The peak, where the peak is difficult to locate. So, but maybe in the future we could work out a better solution. But at the moment, then we don't have a good solution how to estimate the peak. So alternatively, we would use those discrete beta values to say something about the whole profile. So that's why this nonlinear modeling approach at the group level would help. So for example, let's provide some background information. This is nonlinear. Traditional nonlinear, we can use polynomials, right? So that's a popular one. But polynomials is it's a little bit challenging. The good thing is that it's simple, straightforward. The model, I mean, it's once you fix the order for the polynomials, for example, cubic or a fifth or order of polynomials. But the problem is the polynomials are a bunch of challenges. For example, the simplest one, how to decide the order of polynomials. Even if we decide, that's flexibility is still a little bit compromised. So there's a better approach. It's more like data-driven. We don't assume the profile regardless the order of the polynomials. Forget about that. So we use a bunch of basis functions. At the individual level, we use tens or we use cubic splines, but that's still pretty limited. In this case, we use, for example, here I show totally six basis functions. So the simplest one is the black straight line, horizontal line at the top. Then there's the second one is this dashed straight line, right? So that's a linear. Then we can go further, right? Second order, like this shape, then a cubic. So we can increase the extent of complexity. So with six, that will probably would be most of the time good enough to capture the extent of complexity. So that's the concept. How do we use this approach? This technique, I think, was created around the 1990s. It's called using splines, smooth splines, because all the basis functions are smooth, right? So there's no sharp corners. If we use the linear splines, like individual level, those are tens, we would have trouble capture the smoothness of the profiles. So this is the strategy, use different smooth curves, depends on, but we still need to decide the number of basis functions, right? So, but most of the time, 6 or 10-ish, that's probably good enough. So this case, the modern strategy is coded, implemented in the program 3D MSS. So MSS stands for multi-level smooth splines. So there are blog posts to explain how this a little bit detailed. There's a paper at the bottom of the slide that explains the modeling strategy in details. But here we only need to talk about how to specify using the program. Suppose we have, for example, the estimated hemodynamic response function, right? Actually, this is not about hemodynamic, but the age, so longitudinal study. So if we have that case, so we can treat, no, not longitudinal. Actually, I'm sorry. This is cross-sectional. Even in that case, we can at group level estimate the age trajectory. So the age is between individual, not longitudinal. If it's a longitudinal, it will work too. But in this particular case, it's cross-sectional, so we can. The typical way at group level, if you have age, if the age is between individual variable, quantity variable, we just simply include the age as a covariate. So when we do that, we assume it's a linear effect, right? So in this case, suppose the linear effect, especially during development stage, probably linear is a little bit too crude. So you may consider using this smooth spline strategy to estimate the profile instead of assuming it's a linear effect. So in this case, let's look at the data structure at the bottom, right? So this on the left-hand side, on the right column. So first column is subject ID, last column input files. In between, we have two variables. The group, suppose males and females, or child versus adults. Then there's the age, right, for each participant. So those are two variables. So the model specification, MRR, so that's a modeling using a rigid regression strategy. Basically, um, it's a pooling effect, shrinking effect. So we specify the H. The S stands for smooth. The K is the number of basis functions. So you don't have to specify the number of basis functions. By default, it's 10. If it's less than 10, I mean, H values probably you need less based on how many H values you have. So by default, it's 10. So this is like at the group level, population level, that's the profile, the developed profile. The next term is the group difference. The first term is the group cross groups average. Second one is the group difference. So that's the modeling strategy. So we get the profile for both groups average and the group difference between the two. Then we need to explicitly specify the H is a quantitative variable. So that's then we can use create another table to predict the profile because the H value can be a little bit unevenly distributed. There's some gap, and also if we show the discrete values would give us an impression of a zigzags. So we can improve artificially put some finer grades that is for visualization purpose. So to predict estimate the profile will give us a smooth curve, predict the smooth curve, the profile. So the next one, we talk about the role of sample sizes. Most of the time, we pay attention when we design experiment, we pay attention to the number of participants. So if we focus on that power analysis, traditionally we include how many number of participants. We use this strategy, right? So-called power analysis. At least conceptually, we would say more number of participants is better. Better in what sense? From estimation perspective, we get a more precise estimate for whatever the average. Right? If you care about the p-value t statistic, more number of participants, the t-value would be bigger, the p-value would be smaller. Right? How much is the better? So there's a curve to show that. Let's say it's the precision. It's the 1 over the standard error. So this curve is not linear. It's an inverse parabola. So it's more the beta, but the beta amount of beta, the marginal increase is tempers off, right? So it's smaller and smaller. So that's the traditional notion of power analysis. So people tend to ignore the number of trials, but when we design experiment, of course, we need to decide how many number of trials for each task condition. But that number of trials is basically based on some legacy, right? So you can say 20, 30, you may feel enough. So that kind of a thinking is that tend to think the number of trials doesn't matter much. That is tied to another notion because whenever we estimate the beta at the individual level, we ignore the uncertainty. Go to group level, only take the betas. But even if the number of trials matters, right? So that matters only in terms of the t statistic. It doesn't matter about the beta estimate, right? The beta is using the traditional statistic framework is called unbiased, regardless the number of trials. As long as suppose you have 10 or 20, it probably doesn't matter much. It's unbiased, right? So it gives us an impression, since we don't take the t statistic for group level analysis, maybe we can ignore the importance of the number of trials. But in reality, the number of trials matters, and it matters a lot. So that instead of just a single x-axis, it's a more accurately depict through this two-dimensional profile. So the x-axis is the number of subjects, y-axis is the number of trials. If we plot out the relationship, it shows it's the hyperbolic relationship. So different colors, that means different precision or different efficiency. So that means both number of trials and number of participants matter. They matter almost to the same extent. Well, when I say almost, why they matter almost similar? There's an underlying assumption. Assumption that means cross-trial variability versus cross-participant variability. Those two variabilities, which is bigger or they're about the same? So they're based on empirical studies, it shows the cross-trial variability is way much larger than cross-individual variability. It's a few times. For FMI, it's probably close to 10-ish. So that's why, because of the substantially larger cross-trial variability, the number of trials matters a lot. So that's why we need to take care of, when we design experiment, number of trials is also important. Even though the modeling strategy at the group level, we only take the betas, that doesn't mean the uncertainty information about the betas are not important. It's implicitly embedded in the beta estimates. So that we have a paper at the bottom of this slide that shows why, both so analytically and also through simulation, we show that the number of trials matters a lot. So that gives us some sense about when we design experiment. So this slide is a little bit new. So that's our current understanding about the experiment. Let's take a few minutes to explain each item. So the first one, streamer's timing. You may feel a little bit convenient to specify the streamer's timing aligned to the acquisition grades, right? The TR, always like the integer numbers, the indexes. But that's not necessarily a good idea, because why it's not? Because we need to randomize as much as possible. So if we don't align to the TR grades, that will give us more room to randomize the streamer's timing. So when regardless you are using canonical HRF or you estimate the HRF, that will give us more sampling data points. Now, if we fix on always at the TR grades, we may fail to get an accurate estimate at the peak, right? So even if we use a canonical HRF. So that's the first point. So you don't have to, but so that usually will improve the estimability. The second term, it's convenient to use the same sequence, right? Same timing for all participants. Because the software, you use just one timing file for all participants. That's not a good idea either, because one particular sequence maybe have some flaw. Each participant may have a different learning, right, process habituation effect. So you also need to randomize that. So that's another aspect, randomize. So create different streamers timing sequence for each particular participant. That is just a random process. It's not but just some spatial timing. You just need to randomize them. So that's a second point. The third point, well, of course, here by default, assuming the sequence, the timing also need to randomize. In a sense, the inter-trial interval, you need to vary, right? Don't fix at some particular value. There's a program you can use in Japanese, for example, timing file .py that can help you to design that. The third point, trial level sampling is almost as important as the number of participants. We already mentioned that. So that's the third point. The fourth one, interaction effects. If you want to care about interaction, you need way much more sample sizes, both in trials and participants. Why is that? This has been pointed out a long time ago in general, but people tend to forget about this. For example, let me use a concrete example. Suppose you want to compare happy and sad. Happy, suppose for visual cortex, for example, you say happy face, you have the both percent single change is 1%, for example. So that's happy. Well, by default, happy is happy versus baseline, right? So suppose that's the case. Maybe you need 20 participants, 50 trials, maybe good enough, right? That's easy. 1% is strong. But now suppose you want to contrast happy versus sad. Happy in visual cortex 1%, sad maybe 1.2. So now if I look at the contrast, it's 0.2 compared to the single happy is just 1%. Now the contrast between happy and sad is 0.2. The effect magnitude is way much smaller. Now, of course, you need more sample sizes, right? So now suppose we want the interaction. So we want to see the happy versus sad between two groups, patients versus controls. So this is two-way interaction. So now you probably need way more participants. If you want a three-way interaction, that's even more challenging. So that's always think about it when it is experiment. What's your estimate? Estimate is the target of your research topic, the interest. So you need to pay attention whether you want a single effect or contrast or interaction. Interaction is two-way, three-way, right? So the next term is about the HRF, right? So you want to use canonical HRF or you want the data-driven approach estimation. That will have a big impact when you design experiment, right? So what kind of modeling strategy you're going to adopt? So you need to think about that too. So next one, sometimes you think, well, suppose you have patient versus control, right? Or male versus females. Do you need equal number of participants? Right? So usually we say, well, probably should, right? Males versus females, probably equal number of participants probably makes sense. But how about patients versus controls, right? Sometimes we struggle. Patients is difficult to recruit, especially some of those rare disease groups, right? Do we need to have equal number of participants? Well, that depends. If we have some prior information, we know the general population, the control group have way bigger variability versus the control, then we don't have to. The smaller number of participants for the smaller variability, that's probably it's better, more efficient, right? So suppose you would only manage to recruit 20 patients. You may want to feel the urge to recruit 20 controls. But if you know the for the patient group that have smaller variability, you would help to increase the number of control control participants. So the more the better, actually. So that is not equal number of participants is not required when we have multiple groups. Next one. That's probably typical. We always worry about multicollinearity, right? So intuitively, I mentioned 2 days ago. So when we create two equations, they're correlated, right? So it's a concern, especially getting close to 1, the correlation values. So it is from statistical perspective, if they are close to each other, it's difficult to separate, to disentangle them. But there's a cost. If we want to decrease the correlation between two equations, with the fixed scanning time, we're going to sacrifice the number of trials. So those two, we need a balance. So in the end, recent simulation to show that those two opposing forces, actually we don't need to worry too much. Actually, the more trials, that force is stronger than the concern about the correlation between two equations. So the high cross correlation is as long as you don't get it too close to correlation value of 1. I think when you design experiment, don't overstate the concern that problem. So next one, this is about covariates. At the individual level and group level, we always have covariates. When it is experiment, we need to take that into consideration, right? So typical one, reaction time, right? Their behavior covariates. Reaction time is a good idea. Well, in the field, people have been pushing this, right? So reaction time is a good idea. If the association with reaction time is not your interest, I mean, turns out those similar behavior data is not a good idea because it's a downstream. It's not about the trial attributes. So stimulus duration is a good idea because it's about the stimulus itself. So it's a good idea to include to improve efficiency. But the behavior, because it's not about the trials itself, the best you can say is a proxy for the trials, but it's a downstream. So it's not a good idea to introduce, to include as a covariates, typically at reaction time. So I usually don't recommend it because you pay the cost. That cost is a biased estimation. So the last item I want to say is about power analysis. Sometimes, especially when you submit a grant, reviewers may demand that you need to provide justification about the number of number of participants, or the power is 80%, right? So you may feel the pressure to perform. In reality, it's not usually it's even useful. It just wastes everybody's time. Why? Because FMS study is so complex. There's so many components involved, as modeling, covariates, right? So the different pipeline. So the tools available in the field, there are a couple of them, but in reality, I don't think people are use it when they design experiment. Only if they are forced when they submit a grant. That's probably the case. So my point is, power analysis in FMI is just it's not totally useless, but it's not really useful. So that's all I want to say about experiment design. So I think it's time to take a break.
Thanks, Alan. There are a few questions that came in, so maybe we could address some of those quickly. Oh, Gung, are you still with us?
Yeah, yeah, yeah.
Okay, maybe you want to leave your slides just in case you're going to show some. There are a few questions, if I
Okay.
can verbalize those for you.
The reason I want to say but you
Oh,
can
okay, that's fine.
uh,
So the first
which one?
question,
Go
yeah, the
ahead.
first question is regarding 3D MSS, is it possible to include variables like education, duration of illness, age of onset?
Um, what, as long as those variables are between individual variables, yes, including both quantitative variables and factors. So you can include them. For within, it's a bit challenging. So suppose you have two conditions, happy and sad. I recommend that you use it for happy and sad separately. If you want the contrast, get the contrast, extract the contrast first. So then that you can do it. So you do it separately. Uh, so basically, it only allows for between individual variables, both factors and quantitative variables.
All right, thanks. And regarding the hyperbolic relation between the number of trials and number of subjects, um, there's just a follow-up question about which one is more important. So I think I think you said that they're almost the same, but it tilts a little one way because of the RV parameter.
Right. Let me bring up this slide.
Yeah. So I think this is where those vertical asymptotes are.
Where's my?
That's
Okay, there we
line.
go.
Yeah. Yeah.
This one. Yeah. So um, that it's difficult to when we design experiment. It's difficult to see. Um, well, overall, the number of participants is slightly more important. It's tilted to you can say the curve is slightly symmetric. You can also see this dashed line, the gray dashed line, that shows the the most efficient one. So it's also tilted to the number of participants.
Maybe it's worth just unpacking this figure a little bit about what the lines are. So I think so efficiency is kind of one over the expected error, right? So by increasing efficiency, you're getting more precise measures. Is that right?
Yeah, right. Yeah. So,
And
uh,
yeah, each line here is a constant t plus total n, right?
yeah, right. So the different color codes for is the RV, the ratio of the variance. I forget now. Uh,
Yes, that's right because the that's where the vertical asymptote is moving.
yeah, yeah. So different color shows the ratio. I mean, this the reason the number of the trials is important is because the cross trial variability, the variance, how varying across different trials and versus how varying across individuals. So the cross trial variability is larger, but larger, how large? How much larger is the ratio? That ratio is, for example, 2 times, 5 times, 10 times. So different colors shows that variability. So the bigger the cross variability is the different colors. I forget which direction now. It's probably this is a smaller RV. So the close to the origin, this is the bigger one. Maybe the
I
opposite.
yeah, I had
I
to
have to
look
go
up
back to
the
the paper to
I
check out.
okay, I looked up the paper here. I'll put it in the link. So the sigma value is smallest for blue, then larger for orange, green, etc.
Okay.
So you are increasing efficiency by shrinking sigma. So as you so blue is the most efficient of those, and then
Okay.
less efficient is orange. So you're kind of moving from inefficiency with lower T and S or kind of poorer precision. And as you move from red to green to orange to blue, you're increasing efficiency by either adding, another subject or another trial.
So in the paper, on the bottom of this slide, that paper based on one particular data set, we show with different number of participants versus different trials. It's almost close to symmetric between the two. So that's the reason is that because the cross trial variability is almost 10 times, probably close to 10, or some occasionally even bigger than the cross individual variability. Um,
So I guess the idea is if you have a choice to add,
um,
um, yeah,
so
one,
so when I design experiment, of course, we don't know the ratio, right? Which I mean, variability is bigger, but at least this give us some sense. Uh, so there are other consideration. I mean, how much time the participant can stay in the scanner, right? So that well, of course, that you can solve that by multiple rounds. But still, you need at some point you need to fix the scanning time. Once that, then you decide how many trials. Of course, the more the better, right? So then we also discussed earlier about the collinearity issue. Better probably that's less concern, at least that's my current understanding. So I would say pack as much trials as possible based on the particular experimental context. Um, as once you fix the scanning time, so that's the principle. Uh, so that's one consideration. Of course, there's another one, which is how representative are your trials, right? So you show faces, the faces you may need to worry about the males and females, hairstyle, right? So there are many factors. So you need to include as probably broad as possible. So so that's another, not just the number of trials itself, and also the to cover different aspects, different features of the face.
I
So that
wasn't aware that hairstyle mattered that much in studies, I guess, but maybe I guess in the presented image, not in the participant. But I guess the issue is if you have 20 participants with 5 trials each versus 10 participants with 10 trials each, there is actually a little difference in the statistics, right? I guess that's kind of the point of of some
Right.
of
Yeah.
this and that hyperbolic relationship. And
Yeah.
so actually,
Hyperbolic.
probably that people have really emphasized, oh, you need more subjects, more subjects, more subjects. But if you're not getting adequate trial size, you're kind of shooting yourself in the foot and missing an easier way to add more precision or more efficiency to your study.
Right.
I think that might be the take-home lesson here. The there's a follow-up question about what about when you have naturalistic or resting state where you don't have number of trials?
Naturalistic resting state.
Well, basically, you don't have trial count. You just have TRs and things like that. So how does this? Can you extrapolate this when T is not a trial sample size, but you're just putting someone in the scanner longer? I think this might relate to the other paper that came out about this in resting state, like the economics of
Yeah. Yeah. Well,
um,
either whether you treat it as a Wilson study or lateral scanning, you calculate correlation values. So that is still uh, similar, I think, because you are calculating the correlation value. The correlation also is the number of data points is will have impact about the precision of the correlation, right? Even though in the end, unlike the task-based, we calculate beta of the t. In the correlation case, you calculate correlation. Correlation is similar to the t to some extent. But it's a dimensionless number, right? So in that case, there's still precision issue. When you go to group level, that also matters. Uh, so there's a paper that
I'm, I'm
discusses.
putting in the Yo et al. Paper.
Yeah, yeah, Thomas Yo group
Yeah,
in
so I put that
Singapore.
the longer scans boost prediction and cuss cuts. Yeah, I mean I think well go ahead. Anyways.
Yeah, it's pretty much similar. So there's a tool you can manipulate to both the number of TRs versus the number of participants. So increase both, of course, always better. But if one is constrained, you have the option to increase the other. You're not doomed. Suppose your number of participants is fixed. So you can always have the wiggle room to increase the number of trials to boost your estimation precision.
I mean, I think they show something analogous to scan time per minute and number of participants, this kind of hyperbolic thing. So I kind of assumed that I don't know, I don't think they mentioned Gong's paper in theirs, but it's a very analogous idea, I think, and similar kind of results. So I think it makes sense.
Right.
Let me just see if there's another question. So maybe one last question here. I understand about reaction time. What do you mean by behavior like scale rating?
Oh, uh, um, well, the duration, for example, that's each trial have a duration. Is something intrinsic about that trial, right? So that's let me go to which side here. So the stimulus attributes, that one is like duration or like a trial, you suppose it's about rewarding. You show you how much money. But in this trial, you win $5. Next one, you win $7. So that one is also about the stimulus attributes, right? So it's not about how the participant responds to the trial. So this is the upper stream. It's about each trial, something about the trial itself. So in that sense, it is a good idea. It's always to include that will help you. I mean, simply speaking, it's just improve your statistic values. From estimation centered perspective, is about the precision. The behavior of action time, because it's downstream, it's not about the trial itself. It's about how the participants respond. So it's if you draw the information flow, it's not on the information flow directly from the trial to your body response. Even though you may conceptually think it's a proxy, but that proxy, there's a danger. That danger is may create some bias. So that's the problem. I mean, if that approximation is sort of okay, but in reality, the behavior is not region specific. It's, for example, reaction time. It's not about one particular region. That is how fast, how slow you respond. It's the summation of many brain regions. So that other region, when other regions are involved, but in your model, you treat when I use the massive universe approach, the other regions is not in the picture. So that's where the bias comes from. So that's why the behavioral covariance is a little bit risky in that sense. So even though some people have been pushing this, it's typical to say in the literature reaction time by default is a covariate, but in reality we have to be very careful at least to aware of the risk.
Yes, I think that's maybe the summation of today's talk is be careful and beware of the risks with covariance and various modeling features. So, um, okay, maybe we can take one more question, then we will take a break here. So Farouk is asking about the sample size again with regards to number of voxels rather than number of subjects in trials. So yes, our high resolution interest question. When we acquire higher resolution fMRI, we have 8 more times voxels, let's say. So if you double your spatial resolution, you get 8 times as many more voxels. Um, how would this affect your HRF modeling? So, as you move to higher spatial resolution, that number, does that factor into any of this?
Well, if we use the typical massive universe approach, we treat each voxel independently of the rest of the brain, uh, that would have no impact. But it depends. If you go to group level, if the group analysis is the ultimate goal, the impact is about multiple comparison, I guess. Um, uh, that will be smoothness and also probably uh, I never did an empirical comparison, but I imagine probably smoothness is one. Then the total number of voxels, it's not clear how would that impact about the cluster size. Um, if we adopt the approach we are currently working on, create a single model for the whole brain, that probably will address directly to this concern because instead of modeling each voxel separately, then we create many millions, of models. We create a single model that would take the spatial relatedness into consideration. Inside the model, there's a parameter capture that is spatial relatedness. That will probably at least mostly address the concern about the spatial resolution. So that's
I guess
some,
the spatial variability doesn't come into the equations in the same way that like cross-trial, cross-participant does. There isn't like a factor of cross-voxel variability, and that's dealt with, as you say, in this different way of either massive univariate or some kind of the spatial relatedness of all these individual tests and things like that. And maybe that's why it's treated a little bit differently, but it certainly has like important consequences, but maybe just in a different way that can't be put on par with the other two.
yeah. Well, another way is a hierarchical structure, right? So cross trial, cross individuals, those are two different hierarchies. Cross brain, cross voxels is another hierarchy. Currently, the massive user approach, we ignore that hierarchy. Later on, we pay the cost. That cost is multiple testing penalty. So that's the way we currently we live with. So that's why we're trying to address that concern.
More,
Hopefully to include that hierarchy as the single model.
more upfront costs and neuroimaging
Yeah,
analysis. Great.
yeah.
All right, let's take a 10-minute break. So we'll maybe reconvene at 11:15 DC time then.